Rational functions. We are wrapping up everything we know about rational functions. So in this set of notes, we are going to go through everything we've learned so far. We're going to hit on roots or x-intercepts. We're going to hit on our vertical asymptotes and our domain. We're going to hit on the end behavior and horizontal asymptotes. And each one of these pieces is going to come together to help us graph. So what you see here is the parent function of a rational function, 1 over x. I'm also just going to sketch what the parent function looks like. We see this kind of boomerang type shape in the first quadrant, not touching the x-axis or the y-axis because those are asymptotes. And that same shape we see in the third quadrant, again, not touching the x or y-axis because those are asymptotes. That's the general shape we see. But we now know that that shape can be changed, transformed, and even kind of fractured a bit more by the roots, by the vertical asymptotes, and also by the end behavior. So let's dive into what we know, and that is our x-intercepts. We have done this a lot so far this module. Where do we find our x-intercepts? Well, anything in the numerator is going to lead us to our x-intercepts. So let's just talk about the numerator for a moment. When I'm looking at this numerator, I'm asking the question, what makes this numerator 0? And this is where we find our roots. Again, what makes it 0? Look at the numerator and set it equal to 0. When we set the numerator equal to 0, all we have to do is solve for x. This is also called our x-intercepts. It's also called our x-intercepts. So when you see this word roots, another word for roots are going to be our x-intercepts. We're looking right at that numerator because anytime the numerator of a fraction is 0, the whole fraction is 0. And remember, our x-intercept or our roots are where our function equals 0. So that's our numerator. Our numerator mainly tells us the roots. Well, what about the denominator? What is the denominator going to tell us? First thing it tells us is our undefined points in the form of vertical asymptotes. Remember, vertical asymptotes come about when there is an undefined point. Well, how do we make something in these rational functions undefined? How do we make it undefined? It's by dividing by 0. Well, that means we're looking at the denominator. When we look at the denominator, we're asking what makes it equal to 0? Because wherever it's equal to 0, again, wherever it's equal to 0, we can't divide by 0, so our function is undefined. So what we're going to do is we're going to solve for x. If you notice, this is exactly the same process as roots, but this time we're looking at the denominator. So our vertical asymptotes are going to be setting that denominator equal to 0 and finding out where it's undefined. And that is always connected to the domain. So you can think of the domain and the vertical asymptotes as coming from the same place. In this case, they both come from the denominator. Because the domain is asking the question, what can we not plug in? What can we not plug into x? In this case, we won't be able to plug in the vertical asymptotes. So it really is just everything but those vertical asymptotes. Everything but the vertical asymptotes. So when I think about domain, I always think of it as connected to the vertical asymptotes. Whatever we can't plug into the denominator, we can't plug it in because it makes it 0. It makes it undefined, meaning it's a vertical asymptote, and meaning we need to exclude it from our domain. So we're talking about the numerator, that's going to tell us the roots. We're talking about the denominator, that's going to tell us our vertical asymptotes and the exclusions to our domain. Now let's talk about our horizontal asymptotes, or the end behavior. For our end behavior, we have to look at both the numerator and denominator together. Again, we got to look at both the numerator and the denominator together. And that's because we are comparing the degrees. We're comparing the degree of the numerator to the degree of the denominator and asking, is it proper or improper? Because based on that, we have some different rules. Now, if it is proper, we know that we have an end behavior of f of x heading toward 0 on both ends. Remember, they're going to match on both ends. So as x goes to positive infinity, f of x goes to 0. As x goes to negative infinity, f of x goes to 0. Our function heads to 0 or flat along that x-axis in both directions. If it's improper, we have two different options. Improper with equal degrees, we know that f of x is going to head towards the leading coefficient. So let's say that number out in front is 2. As x goes to negative infinity, f of x heads towards 2. As x goes to positive infinity, f of x also heads towards 2. Both are going to head towards 2. But what about if it's improper with a greater degree? In this case, we don't really have a predictable or super predictable end behavior. It's going to follow traditional even or odd end behavior going to positive or negative infinity. And I'm going to go ahead and write even/odd because it really is going to follow that traditional end behavior we learned back in the beginning of Module 3. Now, what is end behavior always attached to? End behavior is always attached to our horizontal asymptote. So each one of these rules we just established should match the horizontal asymptote. I like to think of end behavior and horizontal asymptote as synonyms. They're both describing the same exact feature of the graph. So when I'm asking what is the horizontal asymptote for each one, I'm really asking you to describe the end behavior. So let's describe that end behavior. And again, we've got 3 rules. We have proper, we have improper with equal degrees, meaning equal degrees in the numerator and denominator. And then we have improper with a greater degree in the numerator than denominator. So let's match them up. And they really do mean match them up. Proper, if we had said that f of x goes to 0, well, in this case, we have the horizontal asymptote of y equals 0. For improper with equal degrees, we had said it heads toward the leading coefficient. So that means our horizontal asymptote is y equals that leading coefficient. I'm going to abbreviate that as LC, leading coefficient. And lastly, If we had said that improper with a greater degree follows this traditional even or odd end behavior, it looks like a traditional even or odd function, well, then there is no horizontal asymptote. It's not going to look like the other rational functions we've done before. It's going to look more like a cubic function, a quartic function, maybe even just a linear function or a quadratic function. Essentially, there is no horizontal asymptote. So this is wrapping up everything we've learned about rational functions from the very first day in this module. If we're looking to find the roots, we're setting the numerator equal to 0. If we're looking to find the vertical asymptotes or the domain, we're setting the denominator equal to 0. If we're looking to find the end behavior or horizontal asymptotes, we are comparing the degree of the numerator and denominator. So what are we going to do with all of this? We are going to graph. So let's write some really basic steps to graphing. How to graph? First step is to draw in what we found above. Plot or draw your roots, your asymptotes. Yep, just plot them and draw them. Vertical asymptotes, horizontal asymptotes. Number 2, plug in some points between the asymptotes. And that's really just to see where it's positive and negative. And lastly, connect the dots following the asymptotes. And that's it. As long as you found your roots and your vertical asymptotes and your horizontal asymptotes, you pretty much have everything you need to graph.